All right, today we're diving into a paper that honestly completely changed the game for how machines learn to create. It's this awesome story about starting really, really small to achieve something absolutely massive. We're talking about the 2017 paper that basically taught AI how to dream in high definition.
So really think about that for a second. Can a machine just dream up a face? Not copy one, not stitch pieces together, but generate a totally new photorealistic human face from nothing but random noise? We're talking about a face of a person who has never, ever existed.
And you know what? Back in 2017, this paper showed the world exactly how. But before we get into the nuts and bolts, just look at this. These aren't photographs. No, these are images created from scratch by the model we're talking about today. And they're at a crisp 1024 by 1024 resolution, which back then was an absolute bombshell for the entire field. So to really get how they pulled this off, we first have to understand the huge problems they were up against.
Okay, so why was this such a massive deal? To get it, you have to picture what the world of generative adversarial networks, or GANs, looked like back in 2017. Basically, researchers were hitting a wall, a really big, high-resolution wall.
This quote from the paper itself just hits the nail on the head. The problem was, the bigger the image you tried to make, the more unstable and chaotic the whole training process became. You know, the signals that are supposed to guide the AI's learning, they just went haywire. It was kind of like trying to teach a master painter by just shouting random directions at them from the nosebleed seats in a giant stadium. It just wasn't working.
So what exactly is a GAN anyway? Well, the core idea is this brilliant competitive dance. You've got two neural networks. One is the generator, think of it like an art forger, doing its best to create convincing fakes. Then you have the discriminator, who's like the expert art critic. Its only job is to spot the fakes. And they go back and forth, both getting better and better until, if everything goes right, the forger gets so good that the critic can't tell the difference anymore.
But here's the thing. Before this paper, that elegant dance was, well, it was more of a clumsy mess. Training was just notoriously unstable. You'd get this thing called mode collapse, where the generator just learns one cheap trick. Like it figures out how to draw one okay-ish cat, and then it just draws that same cat over and over again because it's a safe bet. High-resolution images? Forget about it. That was just a blurry dream. And part of the problem was that GPU memory limited you to these tiny batches of images, which just made the whole thing even more unstable. The networks were locked in this really unhealthy fight instead of a productive competition.
So the authors from Nvidia had this wonderfully simple, intuitive idea. They thought, wait a minute, instead of trying to teach an AI to paint a masterpiece all at once, from scratch, what if we taught it to sketch first, and then, only then, add the details? What if you literally let the network grow as it learned?
And this is what that idea looks like in practice. This is straight from figure 1 in the paper. On the left, you can see both the generator and the discriminator starting out incredibly simple. I mean, they're working at a teeny tiny 4x4 pixel resolution. But as training goes on, new layers are added to both networks, systematically doubling the resolution each time. 8x8, 16x16, all the way up to that target of 1024 by 1024.
Here's how that process gets started. The network first learns the absolute most basic stuff, like the general shape and color palette of a face, in this super low-res 4x4 grid. I mean, it's just a blurry blob, right? But once it gets good at that, it gets to graduate to the next level, adding a little more detail at 8x8. It's almost like watching something come into focus, from a complete blur to something recognizable.
So the whole process is this really elegant loop. First, you train that tiny 4x4 network until it's stable. Then you add new layers that can handle 8x8 resolution, and this is the really clever part. You don't just flip a switch and turn them on. You slowly fade them in, blending the output from the old layers with the new ones. This is so important because it avoids shocking the system and wrecking all the progress you've already made. And then you just repeat. Train, stabilize, add layers, fade them in, and keep growing. And the difference this makes is just night and day. Think about it. Traditional GANs had to learn the overall shape of a face and the tiny texture of a single pore at the exact same time. It's an almost impossible task. But progressive GANs, or pro-GANs as they're called, they get to master the big picture first and then they worry about the fine details later. This didn't just make training stable, it also made it way, way faster. We're talking up to 6 times faster, which is a huge deal.
So you can imagine the results weren't just a small incremental improvement. No, this was a total game changer, a complete step change in what people in the field even thought was possible. So let's take a look at the kind of quality this method could actually produce.
Honestly, these images just speak for themselves.
This level of quality, this kind of detail and variation, all at a megapixel resolution, it was just unheard of at the time. I mean, look at the lighting, the texture of the hair, even the tiny reflections in their eyes. The model wasn't just cranking out generic faces, it was creating incredibly convincing photographic portraits.
But it wasn't just the growing idea, as brilliant as that was. This paper was also a masterclass in smart engineering. What you're seeing here is called an ablation study, where they basically add their new ideas one by one to see what impact each one has. The metric here, don't worry about the name, sliced Wasserstein pistons, just think of it as a score where lower is better. It measures how realistic the images are. So the old baseline was at 9.28. Just adding progressive growing, bam! It cuts that number by more than half down to 4.28. But then they add a few other clever tricks, and that score gets pushed down even lower. So the key takeaway here is that it was this powerful combination of ideas that really led to the breakthrough.
And for all you data-driven folks out there, here's the mic drop moment. On the standard CFAR 10 benchmark, the model set a new state-of-the-art record with an inception score of 8.80. This proved it wasn't just about making pretty faces, the method was quantifiably better on the established academic benchmarks.
Now, a paper like this doesn't just set a new record and then disappear. It sets a whole new direction for the entire field, and you can still feel its influence pretty profoundly in the AI systems that we all use today.
You know, if you were to trace the family tree of modern generative AI, you'd find this paper sitting at a super critical junction. So the original GAN idea came out in 2014. For years, it was this really powerful but also really finicky concept. Then ProGAN comes along in 2017, and it's like the key that finally unlocked stable, high-resolution generation. And that directly paved the way for StyleGAN just a year later, in 2018, which built right on these ideas and now powers so many things we see today, from incredible generative art to, yes, the technology behind deepfakes.
And this, for me, brings us to the most exciting part. Because when a paper introduces a core idea this powerful, this simple idea of learn the easy stuff first, then add complexity, you just have to ask, where else can we use that?
Right. So the core insight here was growing the model along this axis of visual resolution, from blurry to sharp, from coarse to fine. But that just opens up a fascinating question, doesn't it? What other axes of complexity could we grow an AI model along?
Just imagine this for a second. What if we tried something like progressive semantic growing? So a model's first few layers would learn super simple concepts: dog, ball, grass. Once that's stable, you fade in new layers that learn relationships: a dog holding a ball. And then you add even more layers for complex scenes: a golden retriever fetching a bright red ball in a sunny park. You see, what started as a clever hack to make stable images might actually hold the key to building much more capable and intelligent AI. By starting small and layering on complexity, we didn't just learn how to make photorealistic images. Maybe, just maybe, we opened up a whole new path for teaching machines to actually understand our world. This 2017 paper didn't just give us pretty pictures, it gave us a powerful new way to think about learning itself.
This is for entertainment purposes only.